1. Okay, last video we have been discussing the Brayton cycle, the ideal one. We have discussed the difference between the open actual one and the closed ideal one. We have drawn these pictures ourselves last video and knew how to depict these states and write them on the graphic side. In this lecture of the video series, in this video, we will do the energy analysis for the cycle itself. We have agreed that we will consider the first process between the states 1 and 2 to be isentropic compression. So, from the ideal gas law and the isentropic relation, we have agreed already that it's PV, the power K equals constant, where K is the ratio between the specific heats, Cp over Cv. And substituting in this relation using the ideal gas law, which is PV equals RT, we get a very important relation, which is P to the power 1 minus K over K times T equals another constant. This one is the one we're going to use during this analysis. Applying it between the 2 points gives that T1 over T2 equals P2 over P1 all to the power 1 minus K over K. During this process, the compressive work is exerted on the fluid. The compressor compresses the fluid, and applying the first law, we get that the compressive work, which is the work done between the points 1 and 2, is H2 minus H1, the enthalpy at state 2 minus the enthalpy at state 1. The same analysis applies at the expansion stage, where work is extracted from the fluid using the turbine. T3 over T4 equals P4 over P3, pressure at state 4 over pressure at state 3 to the power 1 minus K over K. And again, the work extracted is 3/4 without sign convention. This is a numeric value. Is H, the larger H, which is H3 minus H4. This is the work that I get ideally, and this is the work that I exert on the fluid during the compression process, also ideally. Great. Now comes to the isobaric heat addition and the isobaric heat rejection. During these two stages, what's important for us in this analysis, without considering the enthalpy as one of our properties of interest, it can be calculated easily using the temperature at any stage after we calculate it. Because we know that the ideal gas, all the properties of the ideal gas can be defined using one property, which is most of the times temperature. So applying the first law, in this stage, we get that Q23, which is the heat added during the time Qn, which is the heat added during the process between 2 and 3, at the same pressure. It's an isobaric process. So P2 equals P3 equals H3 minus H2. That's great. We're in good shape. This process takes place at constant pressure, so we can view that the difference in pressure is Cp T3 minus T2, which is Qn, a numeric value. Applying the same analysis here, P4 equals P1, and applying the first law, we get that Q14, a numeric value, or 41. We are using just the numeric value, is H, which H is bigger, is H4. We're just using the bigger one to avoid the missing signs. That's it. We know that the law itself is dq equals, sorry, it can be stated like this, but it's the more common one. du equals dq plus dw. you don't have any work. So dq is qn, and usually in thermodynamics we use this sign as minus sign, and we use the work in as a negative work and the work out as a positive one. Because thermodynamic processes all the time needs to extract work, not to import work, while it needs to get in Q, get in heat, while getting out is a negative. So Qn minus Q out equals du, which is, or dH. We will do this substitution when we analyze the further part of the cycle and knew how this is converted into H. X. Okay. Then we deduce that Q14 equals H4 minus H1, the bigger one minus the smaller one, to avoid messing up with the signs. And then we are all good. We can deduce some relations over here. First of all, we're gonna define some dimensionless parameters. The two we're gonna define is the backwork ratio This backwork ratio, denoted as R subscript P, is the work of the compressor that I get into the cycle over the work of the turbine that I get out of the cycle. If we draw the power flow diagram of this cycle, it's going to be something like this. This is turbulent out, this is work produced by the turbine, and this is the work consumed by the compressor. So all the portion that I'm getting from the turbine is this amount. A part of it is consumed in the compressor in order to compress the fluid, the ideal fluid from stages 1 and 2. And what I get in this shaft output is the net output work. This ratio might be very useful in a while. And the second dimension, this parameter we're gonna define is, let me see, okay, it's the pressure ratio. We need the pressure ratio. You denote it R subscript P. This pressure ratio equals P2 over P1, which is the maximum pressure over the minimum pressure. These values always greater than 1 for Brayton cycle. If we use these relations, in addition to this analysis, we can deduce some formulas, which are: the first one we're going to deduce is that given that P2 equals P3 and P4 equals P1, then T1 over T2 is equal to P2 over P1 over 1 minus K over K equals 2. P2 equals 3, P3 over P4. It's about 1 minus K over K, which is equal to, over here, P4 over P3 equals P3 over T4. Then we're gonna invert this, equals P4 over T3. And also this ratio is the pressure ratio. Thus, for conclusion, this is the rule we're going to use when deducing the thermal efficiency of this cycle in a minute, which is that Rp over 1 minus K over K equals T1 over T2 equals T4 over T3. That's it, very good. We're in good shape. In a minute, we're going to use this relation in addition to these two Q's that are get into and out of the system to reduce the thermal efficiency of the cycle. Thank you.